Can't wait to find out what the heck calculus is.
Alright class, today we are going to be starting off calculus by learning about limits and continuity.
So to begin understanding the concepts of limits, we first must understand that delta y over delta t equals the average rate of change.
Winber, is there a problem?
Limits t over delta limits. I told you to stop flickering the lights. God. Limits delta t of, Wait, the door's not over here. That's not normal.
Now, limits and continuity aren't that scary.
No, but they can be difficult for first-time calculus students. That's why we're here, to help you further understand the concepts of limits and continuity. I'm Nick.
And I'm Tiffany.
And welcome to Calc Club. So if you're learning about limits and continuity, then that probably means that you're beginning your journey into calculus. I'm very sorry. However, limits and continuity are some of the building blocks that you're going to have to know before you take this journey into calculus. So without further ado, let's jump right into it. Okay, so the first thing that we're going to have to talk about is average rate of change. This is essentially the change in distance, or delta y, divided by the change in time, or delta t. This can further be expanded into the ratio the function of delta t plus t minus the function of t divided by delta t. Welcome to calculus. I know that this seems like a lot to take in, but it's really more simple than you think. When you're finding the average rate of change, essentially what you're doing is you're finding the slope of the secant line between two different points on the graph. Examples of rate of change can include acceleration, velocity, or any kind of function in relation to time. So let's go to our first example problem. A snowball begins rolling down a hill after an avalanche. Using an acceleration rate of y equals 16t squared, find the average speed during the first 6 seconds of fall. In order to solve this problem, carry out a basic slope calculation. Your first x is 0, and your second x is 6. Plug these x values into the original function to obtain your y values. Once you have these, carry out the slope function. Your answer should be 96. So that's average rate of change, but now we have to delve into another kind of rate of change, and that's instantaneous rate of change. This can be defined as the rate of change at one instant of a function. So essentially, instead of finding an average rate of change or an average speed, you're going to be finding the speed that an object is traveling at a certain instant. This occurs when delta t gets closer and closer to 0, since if it's an instant, then there's no change in time, it's just one time. Let's explain this concept using an example. Find the speed of the same snowball as previously mentioned at the time t equals 6. For the sake of this problem and other instantaneous rate of change problems, we're going to change the term delta t to an h, just for simplicity's sake. It still means the same thing, just think of it as a variable that makes your life a little bit easier. So what you want to do is replace all of the t's in your numerator with a 6. Then, you want to simplify the numerator. Do this by foiling the 6 plus h squared and the 16 times 6 squared. Once the numerator has been simplified, it should be brought down to 16h squared plus 192h plus 576 minus 576. The 576's cancel, and now you're left with 16h squared plus 192h over h. Finally, pull an h out of the numerator and cancel the two h's, both in the numerator and the denominator. Now remember that h is delta t, and you are trying to find the instantaneous rate of change, which exists when delta t approaches 0. So now, replace the h with a 0. This will cancel out that term, and you are left with 192. Now that we've discussed average rate of change and instantaneous rate of change, we can delve into limits. To further understand the definition of a limit, consider the following mathematical equation. The limit as x approaches c of f of x equals L. I know that this looks entirely strange and new to you, but trust me, in a little bit it will make sense. So in this case, take the limit to be L. The limit as x approaches c, which is an x value, is L. The limit in this case, L, is the value that a function, f of x, approaches as x gets closer and closer to c. Let's go to another example to demonstrate. Consider the following graph. What is the limit of this graph as x approaches 2? In other words, the limit as x approaches 2 of f of x equals what? Now this is not asking what f of x equals at this point. Instead, it's asking, what does f of x equal as x gets closer and closer to this value? So as you can see, as x gets closer and closer to the value of 2, it equals 4. Now that you're familiar with limits, consider these 6 properties. Number 1, the sum rule. This rule basically states that the limit of the sum of two functions, f of x and g of x in this case, is the sum of their respective limits. On the opposite side of this, we have the difference rule. This rule states that the limit of the difference of two functions, f of x and g of x, is the difference of their respective limits. Now there's the product rule. The product rule states that the limit of the product of two functions, f of x and g of x, is the product of their respective limits. So we've had sum rule, difference rule, and product rule. I bet you can't guess where we're going next. Constant multiple rule. The constant multiple rule states that the limit of a constant k times a function f of x is the constant times the limit of the function. Now we reach the quotient rule. The quotient rule states that the limit of the quotient of two functions, f of x and g of x, is the quotient of their respective limits, provided that the limit of their denominator is not 0. And finally, the power rule. Consider r and s as integers. This states that the limit of a rational power of a function is that power of the limit of the function, provided that the latter is a real number and L, the limit, is greater than 0, if S is even. So consider these two examples to help understand these previous rules. 1. The limit as x approaches c of 2x to the fourth plus 52x squared plus 2,345. All you're doing is replacing the x's with c's. That's it. That's all. Here's another example. The limit as x approaches c of x squared plus 2x plus 1, that entire function, divided by x to the third minus 6. Once again, you're just replacing the x's with c's. The reason for this is that if c were a number, all you'd have to do is plug that number into the function in order to receive the limit as x approaches that value. At least if the function is continuous at that value, but we'll get into that later. Now for another rule about limits. If f of x is a polynomial function and c is any real number, then the limit as x approaches c of f of x equals the y value of c at that point. Essentially what this says is that if you're given a polynomial function and you're asked to find the limit at a point, all you have to do is plug in this value into the function and you'll have your limit. So for example, find the limit as x approaches 2 of x to the third minus 2x squared plus 5. In order to do this, all you have to do is plug 2 into this function. Upon doing this, you should get 5. So now we've covered the topic of a basic limit, but sometimes that's not enough. Sometimes we split limits into two, into right-sided limits and left-sided limits, or the value that a function approaches from the left side and the right side. Perhaps the best way of understanding one-sided limits is to look at the greatest integer function. That's the function that looks like a staircase. This is a great example of a one-sided limit because there are many points where the graph jumps from one value to another. Therefore, there's no set limit for certain x values such as 1, 2, 3, 4, 5, and so on and so forth. Instead, you can say the limit as x approaches this value from the left side and from the right side. So for example, let's take a look at the following problem. The limit as x approaches 4 from the right side of the greatest integer value function equals blank. Let's also look at the following problem. The limit as x approaches 4 from the left side of the greatest integer function equals what? So for each of the problems that we've done so far, there's only been one limit per x value. But this graph is special because each integer has two different limits, one from each side. So according to this graph, the limit as x approaches 4 from the right side is equal to 4. However, if you look at it from the left side, it's going to equal 3. As said before, the greatest integer function can really help students understand the difference between a left-sided limit and a right-sided limit. So where does this all come into play? Well, understanding one-sided limits can help you tell if a limit exists at a point. A function has a limit as x approaches c if and only if the left-handed limit and the right-handed limit at c are equal to each other. Let's try out another problem involving left-handed and right-handed limits. Consider the following graph. Answer the following questions about the graph shown. What is the limit as x approaches 1 from the left side of f of x? What is the limit as x approaches 1 from the right side of f of x? What is the limit as x approaches 0 from the right side of f of x? What is the limit as x approaches 0 from the left side of f of x? And what is the limit as x approaches 0 of f of x? So let's look at the first problem. So when you're looking at left-handed and right-handed limits, just see where the graph is approaching the question value from each side. In the case of the first problem, x is approaching 1 as it approaches 1 from the left side. However, this is different than the right-hand limit. As x approaches 1 from the right side, it is going to 3. Therefore, your answer for 1 is 1, and your answer for 2 is 3. Now try the next three on your own. Now let's move on to Chapter 2, Section 2, Limits Involving Infinity. So the first thing that you're going to have to understand about this section is what an asymptote is. There are two types of asymptotes, the first one being a horizontal asymptote. A horizontal asymptote is a linear horizontal section of a graph of a function in which no coordinate points exist. So for example, take a look at the reciprocal function. The line y equals 0 of this function is a horizontal asymptote, since no points exist here and the lines steadily approach 0, but never touch it. There are two conditions for which a horizontal asymptote can exist within a function. The line y equals b is a horizontal asymptote of a function if either the limit as x approaches infinity of the function is b, or the limit as x approaches negative infinity of the function is b. Essentially what this is saying is that as x approaches either infinity or negative infinity, it will continue to approach this value, b. It will never touch it, but it will continue to approach it. Hence there is a horizontal asymptote there, a line that cannot be broken. So here's another example to help you understand horizontal asymptotes. Consider the function 3 plus 1 over x. Does a horizontal asymptote exist at y equals 2, 3, or 4? The answer is 3, and you can tell if you look at the graph. When you look at the graph of 1 over x plus 3, you can see that there is no y value equal to 3. As x approaches infinity and negative infinity, it approaches 3, but it never quite touches 3. Therefore, a horizontal asymptote exists at y equals 3. As far as limits involving infinity, their properties are essentially the same properties as any other limit. Just defer back to the chart that you made in Chapter 1, Section 1, except replace c with positive and negative infinity. Next, we have a vertical asymptote. A vertical asymptote is a linear vertical section of a graph of a function in which no coordinate points exist. Kinda sounds like something similar, don't you think? So to understand a vertical asymptote, let's go back to the graph of the reciprocal function 1 over x. As well as having a horizontal asymptote, it also has a vertical asymptote at x equals 0. This is largely due to the fact that there is an x in the denominator of this function, and therefore, a 0 can never exist in the denominator. So we have horizontal asymptotes and vertical asymptotes. So the conditions for a vertical asymptote are the following. The limit as x approaches a from the right side is positive or negative infinity, or the limit as x approaches a from the left side is positive or negative infinity. Here's an example involving vertical asymptotes. Find the vertical asymptotes of the function f of x equals 1 over x minus 3. Describe the behavior to the right and left of each asymptote. So to find the vertical asymptote, you want to find the x value that will make the denominator 0. this value will result in a vertical asymptote. In the case of this function, that x value is x equals 3. Therefore, a vertical asymptote exists at x equals 3. As x approaches 3 from the left side of the graph, f of x will approach negative infinity. As x approaches 3 from the right side of the graph, f of x will approach infinity. Now that you're familiar with limits involving infinity, we can discuss end behavior models. End behavior models essentially describe the behavior of a graph as they approach infinity and negative infinity. There are two different types of end behavior models. There's a right end behavior model and a left end behavior model. Think of it like this. Consider the graph y equals x to the third. As x approaches negative infinity, the graph is approaching negative infinity. On the flip side, as x approaches infinity, the graph will also approach infinity. Therefore, infinity is a right end behavior model for the graph of y equals x to the third. Now let's get into some rules involving behavior models. The function g is a right end behavior model for f if and only if the limit as x approaches infinity of f of x divided by g of x is 1. On the other hand, the function g is a left end behavior model for f if and only if the limit as x approaches negative infinity of f of x divided by g of x is 1. If one function provides both a right end behavior model and a left end behavior model, it is considered the end behavior model. So let's move into some examples involving end behavior models. Find the end behavior model of the following. A. F of x equals 3x to the 6th plus 2x squared plus 21 over 9x minus 10. B. G of x equals 6x to the 7th minus 4x to the 5th minus 8x plus 9 over 7x to the 7th plus 4x to the 5th minus 8x plus 13. Let's take a look at problem A. All you have to do for these problems is take the term in the numerator with the highest exponent and divide it by the term in the denominator with the highest exponent. So, you would take 3x to the 6th and divide it by 9x. This leaves you with 1/3 x to the 5th. This is your end behavior model. Go on and try the next one by yourself. Now we are going to move on to the final section of this chapter. Is it the final?
No, it's not the final section of the chapter.
I don't care. Now we are going to move on to the final section, and that is continuity at a point. Continuity is one of the most important concepts that you'll learn in calculus, so it's important that you understand it. So for right now, think of continuity as a graph that you can trace with your pencil point without lifting it from the paper. This isn't exactly what continuity is, but it's a very basic understanding that'll help you for now. So with this description of continuity in mind, let's take a look at an example. Consider the graph below. Where is the graph discontinuous? In other words, where is the graph not continuous on its interval? Notice how the graph skips at x equals 1. This is a clear indication of a discontinuity. In terms of the definition that you have in your head, you can't trace this graph without lifting your pencil from point A to point B. Therefore, it is discontinuous. Now let's get into the specifics of what makes a graph continuous and discontinuous. A function, f of x, is continuous on an interior point if the limit as x approaches c of f of x is equal to the value of c at that point. As far as endpoints go, a function, f of x, is continuous on an endpoint if the limit as x approaches a from the right side equals f of a, or if the limit as x approaches b from the left side equals f of b. If a point on a function does not abide to these rules, it is discontinuous and it is known as a discontinuity. Now there are 4 types of discontinuities, and we're going to take you through each one and show you an example of one. So the first type of discontinuity is a removable discontinuity. This is a discontinuity in which the limit as x approaches a point on a graph exists. However, it is not the same as the defined value of the graph at that point. Think of it as there's one value from keeping the graph from being completely smooth. You take out one value, and that's a removable discontinuity. Next is a jump discontinuity. This is the continuity that we looked at the first example. This is when a graph goes from being at one y value to jumping and being at another y value. then the graph continues smoothly. Then there is an infinite discontinuity. This discontinuity exists in graphs that have a vertical asymptote. Then there is the weirdest type of discontinuity, which is an oscillating discontinuity. This is a discontinuity in which a graph oscillates as it approaches a point, but it never quite reaches that point. It almost looks like a sine curve or a cosine curve. If any one of these four discontinuities exist on a graph, then that function is a discontinuous function, at least if it occurs on its domain. A function is continuous on an interval if and only if it is continuous on every single point of its domain. So let's take the reciprocal function into consideration. This, believe it or not, is a continuous function. It is discontinuous at x equals 0. However, this is not on the function's domain. Therefore, it is considered to be a continuous function. This brings us to one of the most important theorems in all of calculus, the intermediate value theorem. This theorem states that if f of x is continuous on a closed interval a to b, then it takes on every single value from f of a to f of b. This may seem intricate, but it's actually a very basic thing that you probably already understand about graphs. Let's say that an interval exists between the 2 points of the origin and 5, 5. If this interval is continuous, then it must take on every single y value from 0 to 5. If this interval truly is continuous, then every y value between 0 and 5 must be touched at least once. There's no avoiding it. So remember that one, the intermediate value theorem of calculus. Well, that finishes up our time for today. I'm Nicholas Vespoli. That's a wall. And that's Tiffany Peterson. I'll catch you never again.